The ground beneath your feet feels solid, permanent, unchanging. It is none of those things. Right now, as you watch this, the surface of the Earth is moving, slowly, silently, and with a force so incomprehensible that when it finally releases, it can level a city in under 60 seconds. Earthquakes aren't random acts of nature. They follow rules. They follow patterns. And once you understand the science driving them, you will never look at the ground beneath you the same way again. To understand earthquakes, you have to go deep, literally. The Earth is not a solid rock all the way through. It has layers, like an egg. At the center sits the inner core, a ball of solid iron and nickel, roughly the size of the moon, under pressure so immense it stays solid despite temperatures exceeding 5,000 degrees Celsius. Surrounding it is the outer core, liquid iron churning in slow, massive currents that generate Earth's magnetic field. Above that sits the mantle, a thick layer of rock that behaves, over geological timescales, less like a solid and more like an extraordinarily slow-moving fluid. And on top of all of that, thin as the skin of an apple by comparison, sits the crust, the surface we live on. That crust is not one unbroken shell. It is fractured into roughly 15 major pieces called tectonic plates, along with dozens of smaller ones. These plates float on the semi-molten upper mantle beneath them, driven by convection currents rising from the heat of the Earth's interior. Hot material rising, cooling, spreading sideways, then sinking back down in a vast, slow circulation that has been running for billions of years. The plates move because they are sitting on top of something that moves, and they carry everything on their surface, continents, ocean floors, mountain ranges, along for the ride. The movement is imperceptibly slow by human timescales. Most plates move between 2 and 15 centimeters per year, roughly the speed at which your fingernails grow. But over millions of years, that slow drift has moved continents halfway around the planet, opened and closed oceans, and thrown up mountain ranges from flat seabeds. The Himalayas, the tallest mountains on Earth, are still rising today, pushed upward millimeter by millimeter as the Indian plate grinds northward into the Eurasian plate at a pace no human eye could detect. At the boundaries where plates meet, one of 3 things happens, and each one produces a different kind of geological violence. Where 2 plates collide head-on, one is forced beneath the other, in a process called subduction. The descending plate grinds downward into the mantle, generating enormous friction and heat. This is where the world's most powerful earthquakes occur, and where volcanoes are born from the melting rock forced back upward. The Pacific Ring of Fire, encircling the Pacific Ocean, marks the boundaries of plates colliding and subducting in a nearly continuous loop, accounting for roughly 90% of all earthquakes on Earth. Where 2 plates slide horizontally past each other, you get a transform boundary, and the most famous example on Earth is the San Andreas Fault running through California. Here, the Pacific plate is grinding northwest, while the North American plate moves southeast. They don't slide smoothly. The plates lock together, friction holding them in place, while pressure builds, slowly, relentlessly, for decades or centuries. When the accumulated stress finally overcomes the friction holding them together, the plates lurch suddenly past each other. That lurch is an earthquake. Where plates pull apart, you get a divergent boundary. Magma wells up to fill the gap, creating new ocean floor and occasionally volcanic islands. Iceland sits directly on the mid-Atlantic ridge, where the North American and Eurasian plates are separating at about 2.5 centimeters per year. Iceland is literally being pulled apart, and it is growing new land from the volcanic material filling the gap. The actual mechanics of an earthquake begin at a specific point underground called the focus or hypocenter, the precise location where rock finally fractures under accumulated stress. From that point, seismic waves radiate outward in all directions through the Earth, like ripples expanding from a stone dropped in water. The point on the surface directly above the focus is called the epicenter, typically where the most intense shaking is felt. 2 main types of seismic waves reach the surface: P waves, compressional waves that travel fastest and arrive first, and S waves, slower shear waves that produce the violent side-to-side motion responsible for most structural damage. The Richter scale, More accurately, the moment magnitude scale used by modern seismologists measures the energy released. Each full number on the scale represents roughly 32 times more energy than the one below it. A magnitude 7.0 earthquake releases 32 times more energy than a 6.0. A magnitude 9.0 releases nearly 1,000 times more than a 7.0. The 2011 Tohoku earthquake in Japan, which triggered a devastating tsunami, released more energy than all earthquakes on Earth in the entire previous year combined. We cannot stop earthquakes. We cannot yet reliably predict exactly when they will strike. But understanding the mechanics of plate tectonics has transformed how we build cities, design buildings, and prepare communities in seismically active regions. Every earthquake-resistant skyscraper, every early warning system, every updated building code traces back to the science of understanding what the plates beneath us are doing and why. The ground feels solid, but it is alive, grinding, shifting, and building pressure in the darkness far below, on its own timescale, by its own rules, completely indifferent to the civilization sitting on top of it.